All right, thanks for tuning in. This talk is going to be summarizing a very long-term project I've been involved in, involving a whole bunch of people, with the aim of doing EMRI-modelling to post-adiabatic order. If you don't know what that means, it'll become clear as we go. As I said, this has involved a lot of different collaborators, but in particular, I want to highlight Niels Warburton, who will be giving another talk at the symposium that will present some of the numerical results from this collaboration. Okay, so the name of the game here is self-force theory. So this is a particular perturbative method of modeling binaries. The idea is if we have a smaller compact object going around a big black hole, then the small object perturbs the spacetime of the big black hole. So our exact metric will be the background metric of the central black hole, which will be typically the Kerr metric. And then we have first order perturbations, second order perturbations, and so forth, where the perturbative parameter here, epsilon, is of order the small mass ratio, little mass over big mass. And then we construct a representative trajectory for the small object, titled with Z here, and its covariant acceleration on the right-hand side has self-forces, F1, F2, and so forth, where F1 is constructed from H1, F2 from H2, and so on. Now the first thing you need to ask yourself is how high order do we need to go in these series? And a key feature here to consider is the fact that the inspiral for an EMRI is very, very slow. So you're in the strong field region, typically for hundreds of thousands of orbits, maybe a bit less, a bit more. So that comes from this long time scale, which is 1 over epsilon. So you're dissipating energy quite slowly, so you're evolving the inspiral quite slowly. And so if your mass ratio is 10 to the minus 5, then your time scale is 10 to the 5 orbits. Now let's say we omitted second order and above terms in this equation of motion. So we omit F2, then our equation of motion has an error of order epsilon squared. If you integrate that twice, you get an error in the position, epsilon squared times time squared. And so on this long inspiral time scale, that accumulates to an order 1 error in position, which then translates into order 1 error in your phase. So your waveform phase could be, 90 degrees out of phase with a true waveform for the entire inspiral. Now, obviously for matched filtering, we require much better accuracy than that. We need our errors in the phase to be small, and so that tells you that we need F2, which in turn means we need to solve the Einstein equation for H2, so we need to go to second order in perturbation theory. The same argument would tell you don't need F3. Okay, now the title of the talk was not second order self-force, it was post-adiabatic models. So what does that mean? Well, on the inspiral timescale, this 1 over epsilon time, the gravitational wave phase has an expansion that looks like this. Leading order, it's 1 over epsilon. That's because you accumulate phase roughly linearly with time, so if your time scale is 1 over epsilon, your phase is also order 1 over epsilon. Then you have an epsilon independent correction, and then you have a genuinely small order epsilon correction. Now the typical thinking is that this leading order term should be enough to detect most signals, most EMRI signals in the LISA data. But because you have order 1 errors in your phase, you won't be able to do accurate parameter estimation. But if we have phi 0 and phi 1, then we should have enough for accurate parameter extraction, because the errors in the phase should be very, very small. So this leading order term is called adiabatic order, and what you need for that is the averaged dissipative piece of the first order force. You don't need anything else other than the mode amplitudes of the waveform itself. Now the subleading term is called first post-adiabatic order, and it's determined by the rest of the first order force. So you need the full conservative piece of the force, of the first order force, as well as all the oscillations in the first order force. And in addition to the first order force, you need the averaged dissipative piece of the second order force. So that's how second order and post-adiabatic are in kind of one-to-one correspondence. Okay, now to actually generate waveforms in this post-adiabatic approximation, we use a two-timescale expansion. So the idea here is we characterize the system with a set of slowly evolving system parameters, J. So these are orbital parameters, 3 orbital parameters, the energy, the angular momentum around the spin axis of the big black hole, and the Carter constant. So these are all three are constant for geodesics in Kerr, but now they're going to be slowly evolving for the true inspiraling system. And then you also have parameters for the big black hole. So these are corrections, delta m and delta s, to the big black hole's mass and to its spin, because it's absorbing gravitational radiation, so it is evolving with time, just like the orbit is evolving with time. Then our metric perturbation has this onsatz, this two-timescale onsatz, where you've got these Fourier phases. We have a radial phase, a polar phase, and an azimuthal phase. So these are describing the motion of the small object around the big one on the orbital timescale. So you're oscillating in and out with time, you're oscillating up and down with time, and you're going around and around azimuthally with time. And so all these phases are harmonics of those orbital phases, where these k's are integers. And then you have amplitudes. So for each harmonic you have an amplitude. This only depends on the frequency of that harmonic. So the frequency is the time derivative of the phase, and it depends on this mode number k, this set of 3 k's, and it depends on the orbital, not the orbital parameters, but the system parameters, orbital as well as black hole parameters. So this is the structure of the solution. Then you have evolution equations for how the system parameters are evolving. And so here I use t tilde rather than t. T tilde is the slow time, which evolves only on the time scale of an inspiral, not on the orbital time scale. And then you have these driving forces on the right-hand side that only depend on system parameters and the mass ratio. So these are slowly evolving. Then these phases are evolving rapidly on the orbital timescale. So this, say, psi r would go from 0 to 2 pi over 1 radial oscillation, and psi phi would go 0 to 2 pi over 1 azimuthal oscillation. So you have these frequencies on the right-hand side, and here it's evolving on the timescale t rather than t tilde. So once you put this onsatz into your field equations, the phase factors factor out, and you just solve frequency domain field equations for these amplitudes as functions of the orbital parameters j. Now to generate a waveform, what you then do is you compute and store the first order amplitudes at infinity, so the wave amplitudes at infinity. Typically you don't care about subleading corrections to the amplitude, you only care about subleading corrections to the phase. And you store these as a function of system parameters. So you have a grid of system parameters, and you compute and store amplitudes on that grid. Then you also compute and store the frequencies and the driving forces on that grid. So the frequencies and the driving forces will depend on h2. So you need to solve the second order Einstein equation at each point in your parameter space. But you don't need to store h2 itself, because you typically only care about the leading order amplitude. So then your waveform that you generate is just a sum of amplitudes multiplied by these phase factors, and you've stored the amplitudes as functions of j. So you then just need to evolve j and the phases psi as functions of time. So as I said, j evolves in the slow time, so you just have this O to E. And then we can also write actually the phases as functions only of slow time, so they evolve on the fast time scale. But here I've just introduced this 1 over epsilon to transform from t to t tilde, and the point is these frequencies only depend on the slow time t tilde, because they only depend on the system parameters, and the system parameters are only evolving on slow times. So this is really key, because to generate your waveform, you only need to integrate on the slow time. You don't need to resolve individual oscillations with time. You can take sizable time steps through the parameter space, and you still recover the oscillations in the waveform, because that's encoded in psi A that you are solving for with sizable time steps like this. So you get fast waveform generation out of this procedure. Okay, so first example, what we have been looking at actually for a large number of years now, while we set up this framework, is non-spinning quasicircular orbits. So this is a non-spinning compact object in a quasicircular orbit around a non-spinning Schwarzschild black hole. We now have only one orbital parameter, the orbital radius. We could instead choose the energy or angular momentum, it doesn't matter. And then we still have the black hole parameters, the corrections to the black hole parameters, delta m, delta s. So even if the large black hole is approximately non-spinning, it still picks up a small evolving spin. Then in the two-timescale onslots for the field, we now only have one phase, which is the azimuthal phase of the motion around the big black hole. And that's just an integral of the azimuthal orbital frequency. Now, we published some results for this system last year in PRL, the archive number here. That was not a full waveform. That was the binding energy of the system, which is a bit easier to compute than the waveform, although in some ways actually harder. Since then, we've gone ahead towards getting a full waveform. So as an intermediate, we've calculated second-order energy fluxes at infinity. So this is a plot of the energy flux as a function of orbital radius. So the solid dots are the numerical results. The blue dots are the first-order fluxes, which are kind of standard in the literature. They've been computed by many people many times. Then the new thing is the gold dots, which are the subleading corrections coming from the second-order metric perturbation at infinity. Here, just as an example, where I'm only showing the L equals 4, M equals 4, but we have a whole list of modes, and they all look roughly like this. And here we've compared against the leading post-Newtonian prediction. So the lines are the leading PN predictions for the F1 and F2. And you see, as we go out towards the larger and larger orbital radius, we agree more and more with those PN predictions, as you would expect. And then we deviate in the very strong field. So Niels Warburton will show some more plots like this in his talk. Okay, so just to summarize the current status of things, it's been known for a long time that for LISA EMRI modeling, we need post-adiabatic waveforms to do the kind of science that we've promised that we can do with LISA. The two-timescale method provides a very efficient way of generating these waveforms, and it's actually currently kind of the only game in town for how we're going to do this. The status now of implementing these two-timescale methods is that soon-ish, within the next few months hopefully, we will have post-adiabatic waveforms for quasicircular orbits around a Schwarzschild black hole. And then looking a bit further into the future, we need to extend the implementation to eccentric orbits, and with more difficulty, extend it into a spinning primary, so around orbits around a Kerr black hole. So that requires quite a bit of new infrastructure. As I said, this is part of a long, ongoing research program involving a lot of people. So I'll refer you to some other resources to learn more about the status. There's these two archive papers, but also other talks at the symposium, the one by Warburton I mentioned, as well as a couple by my PhD students, Andrew Spires and Sam Upton. Okay, I will end it there, and thank you for listening.